So hello everybody, and thanks for the organizers for inviting me to give this talk, which is founded in a workshop that we had roughly 2 months ago in Finland, where 47 participants from different research infrastructures globally gathered together to talk about what the in-situ observations mean in relation to EVE initiative. And in situ, we mean the original, the natural site where observations are done. I'm from the University of Helsinki, but I'm also very heavily involved in one of the European initiatives to build up in-situ Earth observation system, which I will be soon explaining a bit more. But I wanted to start with some challenges and quoting Deborah Roberts. I don't know if she mentioned this yesterday when she had a talk, because I couldn't participate in that part of the workshop. But she has stated that the information how physical climate is changing is really important. But what people really want to know, and what will be important and matter for them, is how their lives will change. What is the impact of these changes? So what is the so what element in the climate change story? So we have put together a lot of information how the temperature or precipitation will change in future. What consequences that will have to our people, our ecosystems, and our societies? That's the important question that EVE probably can have and influence and address. To be able to answer this, the need for continuous and comprehensive observations on different kinds of interactions between the planet's surface and the atmosphere are urgently needed. So not only observing the climate and atmosphere, but also what happens and what are the feedbacks to the planet's surface. So my question is, what is the best way to implement this kind of efficient observation system? What should be observed and how? And where should these observations be based on? And how to tackle the heterogeneity of the planet's surface, because we know that not every place is similar. So modeling is, for example, bounded on the heterogeneity. Where are the gaps? Geographical and observational. Where are the gaps on data, accessibility? These kind of issues will probably be discussed in the EVE white paper, I hope. So I'm kind of starting from the integration of research challenges for these in-situ site networks that have been recognized when we talk about the possibilities and observation needs. There's not only climate change that is changing at the moment, we also have the biodiversity loss. We have the eutrophication, we have pollution problems, air quality problems in many places, water quality problems. We have water scarcity or excess water problems as a consequence of climate change. But we also have social problems like environmental protection, sustainable management of our natural resources, water, soils, biodiversity, and ecosystem services. And this calls upon transdisciplinary approach as well. Ideally, and in best case, these all are observed at the same place, same time, same place. Then we can get a full understanding what happens to the system and how it will be impacting the lives of people. The heterogeneity, I already mentioned, the heterogeneity in the Earth's surface is huge. It's not only heterogeneity of the ecosystems, it's also heterogeneity of people's lives, urban versus rural areas, pristine or managed areas, and so on. So taking this heterogeneity into account in models is a challenge. One example that we face in land ecosystem modeling is that for modeling savanna ecosystems and climate change in savannas, the parameters that we use are coming from hard forest. That's in North America. So you can clearly understand that there is something that we are missing from this perspective as well. There are also possibly processes that are not captured, because the processes of the ecosystems are not same everywhere. In Arctic environment or in savanna environment, the climate affects the systems in very different ways in different times of season, and modeling has to cover this diversity as well. There are also challenges in gaps in times and space. So when we observe, for example, the atmospheric composition and climate, greenhouse gas concentrations in atmosphere, they often are processes that happen in 2 to 4 years, the mixing in the atmosphere. The climate system covers time spans of millennia. So that's the sea level respond to temperature change that takes up to 10,000 years. But also the ecological systems have very different time spans. Life of plants may be from very short time, one year or less, to millennia as well. And feedbacks from the system to climate might also take place in a very long time spans and in different phases. So understanding these processes impacts the model structures very heavily. Then we come to the opportunities, and I will now run you through some cases that we have globally and in Europe in particular, because there are already quite a number of observations and things that we can learn from. But first, start with a statement that the group of senior officials on global research infrastructures of more than 15 countries have put together this kind of a body that has set a framework how to promote observations in global perspective. And they stated that their core purpose of the global research infrastructures would be that they address the most pressing global research challenges, meaning that they are the frontiers of knowledge where global critical mass effort to achieve progress is required urgently. There needs to be an efficient e-infrastructure that recognizes the utility of integrated use of advanced data production, data management, and services for accessing, processing, and curating the data that is available, as well as participation and accessibility remotely, not only physically being in the place. Data management, long-term data curation, including metadata, data interoperability, so collecting all different disciplines' data to same place and accessing them at the same time. Data access and reuse, reanalysis of the data that is existing. Alignment with standards and practices, including openness and fair principles, where data is as open as possible, as closed as necessary. Clustering of research infrastructures means that not everybody has to do the same things. When you pool the resources and expertise together, you can achieve more with the same investments. And innovation, technology transfer and intellectual property issues have to be also addressed. You can find in this link their full framework statement, and it's quite an interesting reading. So building upon this framework of a group of senior officials, an initiative has been started in globally. So it's based on the pillars that have to be addressed when we talk about the climate change and different challenges. There has to be a dialogue, there has to be information flow between the in-situ, ground-based, airborne, water-based, shipborne data that is collected in-situ, including parameters that are dealing with biology or ecology, chemistry of the atmosphere or waters, and physics of the processes. So not only one discipline, but all together. And parallelly the remotely observed data that can be scaling from points to regions. And they give the Earth system state, the initial conditions, and the data for assimilation. What models can do is that they can inform the in-situ measurements, what has to be measured where, how, what are the parameters that are still needed, what are missing. And they can also inform the remotely observed data for analyzing the forecasts and predictions. So this triangle, these pillars, they all have to be in place at the same time. So globally, we have, after this group of senior officials, started an initiative that is called Global Ecosystem Research Infrastructure, GERI in short, that is currently having more than 1,600 sites in all continents. There are white places in the map, you can see them very well, so there's still room for improvement. But the main players of the GERI initiative come from the main European Commission initiatives like ICOS, the Integrated Greenhouse and Carbon Observation System, the ELDER, which is the long-term ecosystem research infrastructure, and then from US, the NEON, the National Ecosystem Observation Network, Australia, TERN, the terrestrial ecosystem research infrastructure, and South Africa, the SEON, South African Environmental Observation Network, and CERN, which is not the one that is in Geneva. It's in China, and you can see the blue dots in China. It's the Chinese Ecosystem Research Network that is founded and funded by the Chinese Academies of Science. So these 6 are building blocks of the global ecosystem research infrastructure that has clearly stated aims and processes that they all want to address. Here you see the kind of graph which illustrates which ones do which. Most of them do all those processes and drivers that are taking place in the planet. And just recently, a month ago, we learned that the US National Science Foundation has awarded $1.6 million for the 3 next years to analyze how these infrastructures could work more efficiently together to harmonize the global ecological drought data as a first use case. So a lot of emphasis in the global networking is taking place. In Europe, we are funded by the European Commission, and there's a cluster of environmental research infrastructures called ENVRI. ENVRI is focusing on different domains, air, water, land, the solid earth, and life, which means the biodiversity and ecosystems. There are a lot of acronyms which I don't now torture you with, but you can Google them if you want to know more. ENVRI has, for example, started building an ENVRI hub, which provides integrated services of all these infrastructures together, so that there is one-stop gateway to all the services. There's knowledge base, there's catalog of services, the metadata and use cases, and also access to virtual laboratories. So please go to the ENVRI hub if you are more interested on that. I have 4 examples here of environmental in-situ observation and infrastructures in Europe. ACTRIS, which is the atmosphere, trace gases and clouds. EuroArgo, which is buoys on oceans. ICOS, which is the greenhouse gas and carbon observation system, and ELDER, which is the long-term ecosystem research infrastructure. I tested or collected some information which unfortunately is already outdated. I got some new information just a few hours ago, but these numbers are indicative of the number of parameters, the total investments, and the annual operation costs of these 4 For example, for Actris, there's more than 100 variables. For ICOS, there's more than 70 variables, and for Elder, there's more than 80 variables, constantly measured in all sites. The annual operation costs of all these European environmental infrastructures are something like 300 million euros, which is less than 10% of the costs that are incurring from the real CERN in Geneva. So you can, from those numbers, maybe calculate how small investments or small sums of money are actually needed for doing really good environmental observations, and having more investments would of course improve this situation even further. One example of what this infrastructure can do is given here as the soil drought observations that are done on one spot here or a couple of spots here in Germany, on the Terreno national network of terrestrial observations. When you do continuous observations, you can of course get the situation right now. But when you do automation campaigns and install new observations, you can also scale with space. And then regionalization of with models in time and space, and forecasting in time when you do have the previous situation and reanalysis of the models, of the data with the models. So this is the thing that the observations can provide for improve the models. We also need to account for all the domains, including the human and social domain, and this is what I started with. The holistic approach is needed. We need observations not only on the climate or waters, we need also observations on the social and economic sphere, what happens in the systems when, for example, land use changes or economic conditions change. So one example is the ELTER, which has a hierarchy of site categories that cover these 5 spheres. All the sites, all the 500 sites have to measure with harmonized methods the atmosphere, the social and economic sphere, the biosphere, the hydrosphere, and the geosphere. And this way, ELTER will serve many research communities by providing access to facilities, the sites, information clusters, collecting information on standard observations, but also remotely observed data products, analytical tools and virtual labs, and of course training for observers, but also modelers. One example of a site that is planned for integration is given in this graph. That's the station for measuring ecosystem-atmosphere relations that is hosted by University of Helsinki and is situated in southern Finland. It's been operating since 1995, and the purpose of the site is that it combines the ground-based data, remote data, and multi-scale models. So far, it's been contributing to about 50 or more European scale projects. Its ongoing measurement scheme is covering more than 1,200 different parameters, 1,200. And out of those, temperature is just one parameter. The data flows 24/7 and 365, and the data numbers are quite huge, so it's 10 billion points, 1 minute time resolution, and 700 billion points, 1 second resolution, including the eddy covariance 10 Hz flux data. It can be implemented in different ecosystems. The SMER2 station is in forest, but its in vicinity is also a lake site and a peatland site, and it has been implemented in urban areas and also in agricultural areas recently. And in that site, the purpose is that all infrastructures are welcome. So Actris, ICOS and Elder work there hand in hand, and we have recently also installed or joined into the GO measurement network. So the outcomes of the workshop, where 47 people participated and discussed 3 days quite intensively on what should be the message from that community to this meeting and the EVE process. We want to emphasize that there are a lot of existing assets. We have the European Research Forum infrastructures, the ESFRIs, we have Copernicus, we have GCOS, we have WMO that has several different initiatives of observations. And then we have the cluster initiatives like the GERI or the ENRI, which pull things and domains together. But we also identified gaps. In particular, the gaps are in Global South. We also recognize that oceans are not as well covered as they should be, and the biodiversity observations are very much also in development and need more emphasis. We discussed heavily about how to improve the situation in Global South, because we recognize that when we have invented methods or processes or tools in Europe, in Western countries, developed countries, just importing them to the Global South is not the way to do it. It has to be done differently. It has to be done on the conditions of those people living there and doing their research there. So collaboration, networking and training and helping each other understand what things need to be done. There's also gaps in standards and common data access, continuity of data sets, opening of data, so improving the interoperability and addressing the complexity is important, including impacts of human and social systems, citizen science maybe, agent-based modeling was mentioned yesterday as well. We have some important message for the national and multinational investments, because they can be used more efficiently when collaboration is done more efficiently. We discussed a bit about AI and expansion of new measurement systems and dialogue with the stakeholders to promote this integration, harmonization and use of data. But the key message is that we need to show how to work towards the solutions, and the research infrastructures represent a major building block of pre-investments. So thank you for all the workshop participants, and here is a smiling picture of the people who participated. Thank you.